Welcome back to our video module on dynamics. Let's pick up where we left off. Last video, we finished up talking about position and polar coordinates using the unit vectors for polar coordinates, and we identified an equation for velocity in polar coordinates. One further thing that I should note is one of the ways that we found the velocity, we spent three different ways. One of the ways is we took the derivative of position with respect to time. Today, we'd like to use a similar approach where we identify the acceleration vector in polar coordinates by taking the derivative of the velocity vector in polar coordinates. Now, this full definition for acceleration can be very unwieldy at first, so we're going to start off finding the acceleration if the radius is a constant. So that's going to, in our velocity, that's going to take out this term. There's no change in the radius or the distance from the center. The only thing that we're going to see a change in is our r theta dot e theta. If we take the derivative of the velocity with respect to time, we have a solution that goes r theta dot squared in the radial direction plus r theta double dot in the angular direction. And this comes from simply applying the chain rule, maintaining radius as a constant, or the distance from the center as a constant. This is the acceleration of a particle moving in a circular path. So let's make sense of these two terms. The first term, we see a combination of angular velocity and radius. We've seen this before in the form of omega squared r, and that is our centripetal acceleration. This is what causes the tension in a rope when you're swinging a rock above your head. The second term is our angular acceleration. We have a theta double dot here. This refers to, and we see this often when we look at r alpha. This is the additional acceleration that you might experience if you're trying to swing a bat. This basically is speeding up to some constant velocity. And let's say you swing that bat and you just keep on swinging it at the same speed, going in circle and circle and circle. Now you're feeling only the centripetal acceleration. When you start off, you're feeling the angular acceleration. These are the two components of our acceleration in a circular path. So in summary, we want to look at the full acceleration in polar coordinates. Today, we started off with only looking at the acceleration in a circular path. We see that it has two components, the centripetal acceleration and the angular acceleration, and we already have an intuitive understanding of what those mean. In our next video module, we're going to remove the circular path requirement and take a look at acceleration in full in polar coordinates. I look forward to seeing you then.